is from the Institute and is doing his PhD at the University of Bremen. And will tell us a little bit about the Polarstern voyage that we were on together with Jody on the geophysical data from there into the Vincennes Bay.
Yes. Yeah. So also, hello, everyone. So I'm going to be talking mostly about, exclusively about Vincennes Bay and basically how the continental shelf developed in that area and went through changes through glaciation and also before that. So how it developed from the continental breakup a little bit and then all the way to the geologically modern times. So first of all, where are we and what are we doing? So Vincennes Bay is located in the very most western section of Wilkes Land, so in the Knox Coast, and the most prominent feature there is actually the Vandervoort Glacier. So you can see here. There's a pointer. Nice. You can actually see here a map of the Vincennes Bay area with the Vandervoort Glacier located on the very west of Vincennes Bay, and this is actually the glacier with the most ice mass loss in modern times that are currently observed, and which begs the question: what actually happened here in the past? So we're trying to investigate the past behavior of this glacial system with seismic reflection data that we have collected during the voyages PS141 starting from Hobart in 2024. As well as some older Russian data that has been collected in 2021 in this area, and all of the seismic lines that are available in this area are also here on this map. So the black lines are the PS141 lines, and the dark gray ones are the older Russian lines, as well as some legacy data that's here in this beigey color. And the aim of all of this is to reconstruct the major glacial advances and also reconstruct the depositional environments that all of the sediments on the continental shelf have actually been deposited there since the onset of southern glaciation. And this actually provides, this data set actually provides the first data on pre-quaternary ice sheet dynamics in this region, which is quite exciting, I must say. And how we actually trying to get at least the H model onto this continental shelf. You can see here in the upper right map, there's a few orange dots there. That's all the scientific drill sites that have been collected in this area, and there's a distinct black in the region of the Knox Coast, or like the western Wilkes Land. So that would be nice to have more data there, but here we are. So we have to correlate seismic horizons for quite a while, and you might ask yourself, why should we care about the really old stuff? So here you can see the global average temperature compared to the modern times from the late Cretaceous all the way to modern times. And we can see here the transitions of the climate has done from a hothouse in the Paleocene, Eocene, that then transitions to a cool house in the Oligocene, Miocene, and then finally to a ice house in the Pleistocene, roughly. And then we also have the modern climates or global average temperatures on a different scale, and also future projections. So if we compare the future projections, if we don't take the very grim ones, they are somewhat consistent with the climate that has been going on in the Oligocene and Miocene. So these are actually quite good climate analogs for our future projections, which is, that's a nice thing to know how that actually might look and inform the modeling. And before we get into it, because I don't know who has that much background in seismics. So the basic principle is just we have an air gun source, we create sound waves that penetrate into the seafloor, and those get reflected by density contrast in the sediments. So we get these reflectors that we can then interpret for structures and the sediment structures, and also the depositional environments following the that are characteristic for these sediment structures. And this then enables us to actually recreate or like get an idea of what the depositional settings were like and how the climate by an extent was like during that time in that area. And that was the very fast crash course. And this is basically a few little pictures of the stuff we've done. So we have here the collection process on the voyage. So we have this. We have the source. So there's the air gun there. There's me pretending to work. And then we also have the SEMA that CSIRO lent us very graciously. And you see, it is a bit cold. But if we do it a little bit, if we do like actual seismic surveys, it is a bit monotonous. This is like 50% of my camera roll from that entire trip, but it is quite nice. And you can actually then get really nice pictures. So this is actually now the first seismic cross section of the area. So this is a Russian line going from the deep sea. We can that is here on the left hand side in the north, all the way to the continental shelf here on the right. So you can see here the colored lines. Those are horizons that are coming from deep sea drill sites offshore that we correlate onto the continental shelf, and we can see that it actually worked fairly well. So we have horizons from all the way from the continental breakup. This is the lowest ones around 83 million years ago, and to that then continue onward through the late Cretaceous, Oligocene, Miocene, Pliocene to the somewhat recent times, like 5 million years ago, and then maybe a little bit further than that. So we actually see, if we just look at this continental shelf, basically two general, let's say, facies. So we have this well stratified sediment that is very shallowly dipping and is located mostly on the middle continental shelf. And we have these steeply dipping prograding strata on the outer continental shelf. These are most likely glacial, and the well stratified is the pre-glacial stuff. So with this, we have at least a good age model, and we can now try to actually interpret what all of these nice horizons and these lovely wiggle traces actually mean. And if we take a look at the middle shelf, so this is one of the lines in the closest to the Van der Vaart Glacier that we've collected on PS141, and that's just for future reference. I've put a time scale there, so you know where we actually saw roughly in the past. It's always kind of on the right.
Timo,
yes.
Maybe you have to click something that this meeting is being recorded. Actually, then you can see the time scale a little bit better if there's something that you can click.
That's just the late Cretaceous. We can ignore that. At least for the most part. That's a now me problem, not a past me problem. So, but basically we have here in green, that's like the late Cretaceous stuff, so the continental breakup and a little bit and a bit past that, and then here in the dark blue we have the Oligocene. These are the Eocene. So between 65 million and 34 million years ago. And these are these shallow dipping sediments we've seen before. And this is actually within these strata we actually see some erosional features. These are these fluvial, or like these channels. We have these U-shaped, or at least somewhat U-shaped erosions with these reflectors that go inside of these channels, or these shallow erosions. And what this then actually means, these are fluvial channels. So we have likely an alluvial plain that is depositing sediments here, and then channels carving into that. And if we look a little closer onto our channels, what can we actually see here? So all of these imbricated progradations, so these small reflectors that are inside of the channel, these are actually point bars. So what this means is if we see point bars, there's a channel that is meandering. Because if a fluvial channel goes from side to side, because that's just what fluvial channels in a specific environment do, you get these point bars deposited on the inside of the turns, and we actually see something here because we have erosions in there, and then we also see like building up of the alluvial plain. So you have a change between aggrading and degrading channels. So this is indicative of within this time frame there's a change in sediment supply or water supply happening, and this points towards something. I'm not quite sure yet, but hey, it is an interesting observation. And pretty cool. So we can now look a little bit further and actually look at glacial stuff. So we can say if we look into the Oligocene, and specifically the late Oligocene, we see again somewhat stratified sediments, but now we see different behavior. So if you look at the zoom section down here, you can see these channels where we don't really have any features inside of them, and it's just like this very chaotic facies. But then we also see these progradations, like these small scale progradations on one of those reflectors. That means that's not a fluvial like a fluvial feature anymore. This is rather a delta. So where the channel just takes sediment and deposits it at the mouth of the channel. And we also see like sections where we have these deltas, and then we have very long stretches of rather stratified sediments. So what this means in this context is we actually have outwash plains. So this is basically when we have a glacier sitting somewhere in the back. That's a glacier then, like it has meltwater, it creates fluvial channels and outwash. So when we have just the normal like fluvial discharge, we create like braided river deltas that are being deposited at the mouth. You can see that here in the diagram on the top right. We have like an outwash plain that is very shallow, and then we have these progradations that are being deposited. So that is here on the seismic section. That those are these small, for instance, these small progradations over here, and this then when we have a flooding event, so like when there's like a dam breakage, or we just have a lot of meltwater discharge from a glacier sitting in the back, we then get a lot of sediment transported. We establish new flow paths, new channels that are then carved into the underlying sediment. Those are the channels we can see here, like here in the blue U-shaped thingies. These are then actually continuing to the while the outwash flood is happening. We get these large deposits going on for kilometers at a time. This is very similar to things that are happening, for instance, in outwash plains on Iceland. I'll butcher the name. So the Sando Plains in the south of Iceland. And when this outwash flood is over, we have established new channels, and where we have braided river systems in there again depositing delta sediments on the edge of our outwash plains, and this then creates these very distinct terraced looks, where that is very distinct, where you have multiple aggregating outward planes on top of each other, and then having a steep break to the actual end of the outward plane. So if we look back onto the middle shelf, we actually can see some more interesting stuff. So we can see these channels carved into those outward planes, but these are very deep and somewhat broad channels. You can see those here marked here in the lower section in red, and these are actually, because these are so deep and also wide in this case, they are morphologically very similar to tunnel valleys. So these are subglacial channels that are carved underneath an ice sheet. That's where you have meltwater discharge that is just carving away sediment. And this is actually the first indication of a grounding line on the continental shelf. So not somewhere in the hinterland where you have like alpine glaciers and stuff, but now we have an ice sheet sitting on the continental shelf that is likely also marine based. So this is around 24 million years ago at the transition between the Oligocene and Miocene. And this is at least somewhat later than has been mostly postulated for the East Antarctic Ice Sheet. And we can look at these tunnel valleys also here in another cross section. So you can see here on the left a cross section of one of the largest tunnel valleys. So these are really deep. This is like 300 meters deep and about 7 kilometers wide of a channel. So there are actually a few features we can see in there. So we can see like multiple incisions. We can see slumps on the side. We can see channel widening. We can see a little bit of sediment deformation down here. And this is actually indicative of a few different ways tunnel valleys form. So the first one, so how large tunnel valleys got established, you have this, you have outburst flooding. So something we have already observed, or we have already postulated before. I don't know if we can say observed per se, but yeah. So if we have these outburst flooding, so we have a lot of sudden discharge, and we deposit these large outward trends, which we can also see on some of the other profiles. And then after we have this sudden outburst flood where we establish these giant tunnel valleys, we then get some other steady state formation. So we actually see these multiple incisions. That's then when you have just meltwater discharge that is coming from like general melting and flowing into these tunnel valleys, carving multiple incisions into these tunnel valleys and also widening the section. So this is then the multiple incisions we have here, as well as some channel widening. And if we see these, look at these sediment deformations, that's also something we can attribute to where there's just not a lot of meltwater coming in, but there's still water, and water is being drained from the ground actually and deforming the sediment, and then just being squeezed out by the weight of the ice sheet. So one other thing you might see here, there's actually two different generations of tunnel valleys. So you see the first one here in as a black line, and then the second one in a bluish line. So this actually also means there's a preferred flow direction, or these are at least getting reactivated because we have this filling of the channel, and then it is getting carved into again. So what does this mean? So we have these two generations, and basically we can map them along one horizon. So they're always on the same horizon. There's not really like the two successive horizons. So this is like the 24 million years ago and like one a little bit above that. And if we try to correlate them over all of our seismic lines, we actually get a flow direction here on the right-hand or upper right-hand side. You can see that there's three distinct channel systems. We have one in the west, one in the center, and one in the east, with the central one being the largest one. And since these are getting reactivated, we can say that this is a preferred flow direction of these channels from the southwest to the northeast. And since tunnel valley, or like subglacial flow, not generally follows the hydrostatic gradient underneath an ice sheet. That also indicates the general ice flow directions. So it's likely coming from the Knox coastal plain rather than from the Vandervoort, Glacier, where we in modern times see the main ice flow coming from. And this then actually, this then actually shows us that there is a change in ice sheet dynamics happening here in the somewhere in the Miocene. So we're looking at the almost last slide of this profile, I promise. And after these tunnel valleys, we actually see marine conditions. So what does that mean? We have a glacial retreat after the establishment of tunnel valleys. Stuff is melting. The glaciers are retreating backward, and we just have normal marine deposition. And on top of this marine deposition, we have these very chaotic wedges. You can see them here with the pointed to, and there's like these not really any reflectors visible, but distinct wedges. So these are actually till wedges that is glacial deposit that is just bulldozed by an ice sheet advancing, and that's all the reworked material being deposited at the front of the glacier. So this is then again an indication of an ice sheet, a grounded ice sheet present on the Vincennes Bay continental shelf. And this is then actually the start of the full glacial conditions in this area around 40 million years, or like slightly before 14 million years, likely during the Middle Miocene climatic transition. So we can now move on to another profile. So if we can see here the outer shelf. So we have now moved a bit further to the east. West. And we can see here again those fluvial and glacial fluvial deltas and those dimictic or glacial wedges here. And from that forward, we actually just see this steepening trend of our progradation. So where the sediment is just building outward, the continental shelf outward. And the steepening indicates that there's a lot of sediment coming in to a continental shelf and being deposited there. And we can see approximately 30 of those sequences. And all of these sequences are cut off at the top, where you can see those truncations of those reflectors. They're all terminating directly at the seafloor. And normally, if we have like normal continental shelves or also Antarctic continental shelf, we expect topsets on this continental shelf. So topset sediments on top of the continental shelf that are just being deposited by glaciers just by outflow and hemipelagic sedimentation here. These are not really present. So that means there actually have been, we either had one very large grounding zone advance where just everything got bulldozed, or we have multiple grounding line advances that are coming in quick succession, one after each other, where there's not really enough time to deposit enough sediments that these are not getting eroded with the next glacial advance. And this sounds a little more likely, and I will tell you why. Because within all of these sequences, we see actual glacial deposits again. So most of these 30 progradational sequences, there are glacial deposits present. So you can see those here in the middle Miocene. You can see these chaotic phases right here, as well as on the outer shelf at the end of the middle Miocene and going to the Pliocene, where you have these chaotic wedges on top of the rest of our sequences. And this then means there has been a glacier at least present in most of these sequences all the way to the continental shelf break, so extended all the way over the entire continental shelf. Meaning these are most likely all glacial. And if we look a little closer at some of these sequences, we see three distinct phases in these sequences. So we have these the local aggradation. We have that's those reflectors that onlap onto a lower boundary and also downlap onto the same boundary, as well as some very parallel reflectors and that are truncated for the most part at the seafloor, and these glacial wedges I've talked about before. So if we create a series here, how does that actually work? So at first we have an ice sheet on the continental shelf edge. We get this. We get the position of our diamect when the ice sheet advances, and we get a little bit of erosion. So we have this lower boundary, and on top of this lower boundary, we get this local aggregation. So these are the outwash muds that are coming from the glacier, being deposited on the continental shelf edge, or like at the continental shelf edge, also onto the slope. And if this glacier is constantly eroding, we are eroding most of the top sets, and when this retreats, we get a deposition of our topset sediments, because now we have accommodation space here to deposit sediments. And when this glacier then inevitably re-advances, we again have this erosion and transport of our topset sediments here on top. So this gets then eroded. We again get one of these diamectic wedges with those downslope gravity flows and erosion happening, creating the topmost erosional boundary. So now we have to move again to the first one, to the middle shelf, because there's one thing I have not really talked about, which is this giant wedge on top of everything. So this is the stratigraphically youngest stuff. So this is deposited somewhere in the Quaternary, and this is somewhere below 5 million years ago. This is actually the topic of one of my colleagues working on this data, like Tobish. She has made this lovely diagram that you can see down here, how the deposition works. So we basically have the ice sheet that is eroding and reworking a lot of sediments, depositing it like just below the grounding zone, and then basically by a continuous re-advance, building this grounding zone wedge further seaward, or ice distal rather. So what does this actually mean for our purposes? We have this means that we had a continental shelf wide spanning ice sheet that then retreated somewhere in the Quaternary to this point, somewhere on the middle shelf, where we now are depositing massive amounts of sediment, and having a general grounding line stabilization before it then the ice sheet then retreated further backwards to its modern extent. Yeah, and that has been, we've now taken a lovely stroll through the development of the continental shelf, and now just to conclude everything and sum it up once more. So basically, we have these fluvial systems that have been present in the late Cretaceous to Eocene, where we have these meandering channels and fluvial deltas that are shaping our continental shelf. And then in the Oligocene, we have the first indications of some glacial influence, where we see outwash plains with these outwash deposits building up the continental shelf for the most part. That is then even further expanding the ice sheet. So we can see the grounded ice sheet going onto the continental shelf, creating these tunnel valleys we have seen around the 24 million years ago. And these are likely, so this ice sheet is originating from the Knox coastal plain rather than from the modern Vanderbilt glacial outlet. And after we have established this ice sheet, it retreats again. We have like a warmer climate, so the ice sheet retreats, and after the or at the start of the early Miocene, we actually see the establishment of full glacial conditions. So now we have an ice sheet that is mostly coming from the Vanderfoot Glacier region, depositing sediments onto the continental shelf and eroding most of the inner and middle continental shelf. And this actually then shows us that we have, and afterwards then retreating again in the Quaternary to the creating the grounding zone wedge, and then further to the modern extent. And this actually shows that there actually has been a reorganization of the ice sheet somewhere during the Miocene, where where the ice sheet it changed ice flow directions for some reason. I would also like to know why. But that's a future Timo problem, or just generally a future problem. And with that, thank you for your attention. Some nice pictures of the cruise with the seismic crew. Some nice glaciers, Polashtian, and an obligatory penguin. Thank you. Any questions?
Thank you, Timo. Does anyone have any questions also online? There are lots of hands going up online, like floating. It's really cool.
Nice.
Oh, go ahead.
I have a question. Thanks. That was a great talk. There's very prominent wedge. Is that whole wedge a grounding zone wedge on that thing on top that your colleague is this down? Yes.
This one, yeah. So this entire wedge here. So everything that's in this bluish purple thing on top of here, that is the entire grounding zone wedge. So that's actually one of the largest ones found. So that's 65 kilometers wide and almost 300 meters thick.
Okay. Well, so my question is actually, I'm just surprised that it seems to be very little quaternary sediment outside of that wedge. So a massive wedge was formed. Where is all the remaining quaternary sediments, and how did all that material get there if it's not in other places?
So likely the ice sheet has been extended all the way to the continental shelf edge quite recently, because there's not really any sediment on top of those truncations. It had to be very recently, so maybe even since the LGM. So but why then there was no deposition on top of there, either because most of that sediment is deposited in the grounding zone wedge since the last retreat and didn't really move further out onto the continental shelf, or it got swept away, which I find a little unlikely. But my working theory is that it was just very recently all the way to the continental shelf, so it extended quite far, maybe even post LGM that it extended this far and then retreated quite rapidly.
Thanks.
There's one question by Jackie, and she's in the lab, so she won't unmute. Great, Timo, thanks. How was your resolution in the Pliocene, especially in the mid-Miocene warm period?
In the mid-Miocene?
That's 3.3 to 3 million years.
Thank you.
Thank you, Jackie, for putting it on that.
For this, I will go back to this graph, so you can see that the last the last horizon we can see here, that's the correlated from the deep sea. That's 5 million years ago, and after that we have two, maybe three sequences. So we cannot really date these, when these glacial expansions actually extended all the way to the continental shelf edge. only thing we can say, there have been likely 3 extensions all the way to the continental shelf edge. So actually resolving this with a age is, at least with this data set, somewhat impossible. But there have been at least 3 advances to the continental shelf edge from.
So would you recommend a series of piston cores along some of those horizons then to try to get some similar stages?
Maybe even further. So the problem with piston cores is
Exactly.
no, they are actually not really penetrating in this stuff because this is very very well consolidated sediments. We tried to get piston cores there, but it was honestly impossible. That the best thing we had was like this much in one of the core catches, which could not be dated. So you would have to get a proper drill for this, and maybe something like Mibo, and just do a transect along that, so you actually get some age control on most of these horizons.
And thinking that it's right in front of Casey, I think that's a worthwhile cause, right? So go ahead.
I really found those tunnel valley features interesting. That seemed a lot wider than I would expect subglacial hydrology systems to be. And I'm wondering, you may not know the answer, and in which case I apologize, but are there observations of modern parallels, or where it's kind of that broad, or is this indicating somewhat different ice sheet?
So these tunnel valleys are approximately the same size as the Vandervoort Glacier Trough. So we can expect something along these dimensions, probably within this time of this where these tunnel valleys are carved, at least from the mass of ice sheet and subglacial discharge. And recent examples of tunnel valleys this large, the most recent ones I know of are in the North Sea, where we have these giant tunnel valleys with 12 kilometers to 500 meters depth. So they exist. These are not the largest ones. I think there are also some observed on the eastern Antarctic margin. I'm not sure where though, but they tend to be a little smaller than this. So there is definitely something happening with the ice sheet, so that there's, for some reason, it's first of all coming from a different direction than we would expect, and there's way more meltwater discharge from specifically this area of the Knox coastal plain and Knox coast. For some reason, maybe probably a very different discharge system, that there has been something changing during the Miocene. Maybe the spitballing here, but maybe the Aurora subglacial basin wasn't really filled up yet completely, so that there was just not really anything coming from this direction, or just large reorganization of the ice sheet. Yeah, I hope this answered your question.
Question. You show a picture with the tidal influence as well on the groundings on wedges.
Yes.
How would you compare the time scale of the tidal influence and the groundings on wedge formation, and also the grounding line migration? Because they have very different time scales, right?
Yes.
The groundings on wedge to be formed need many, many years, and the tidal is hourly. How would you compare these time scales?
So something we don't really know how fast the groundings are actually formed. The best estimate, that's the work Chiara Tobish has been doing currently, and she's writing the manuscript up right now. So that's she estimates a 4,000-year growth of this groundings on wedge in particular. So there is there is a different time difference. So you just have the tidal influence is basically just compacting the sediments below that and also eroding it. but how far it advanced and retreated, we can't really say without cores. And problem was there's no real cores on the groundings on wedge because it is very compacted and we could not penetrate that with a piston core. MEBO. We need MEBO.
We need more.
Go, go. Anyone else? Any other questions? I think so. Timo, you're still around until Christmas. If anyone wants to have a chat, look at nice pictures from Polarstern and all of that.
So I promise you, I will not show you just pictures of the A frame.
Thank you very much. It's a good picture of Polarstern.
Yeah,
It's a good picture.
yeah, it's good.
How's things, Joe? Did you yawn? I had a yawn during that session.
Just then, only just then.
All right.
Yawn, oh, I have to go back to my own work now.
Yeah, right. Yeah.
No, no, it's okay.
That's right, that's how it's supposed to work, right?
Put it down and